All right, I think we'll get started. So welcome everybody. This is our Alumni and Friends seminar series for the Department of Civil, Environmental, and Architectural Engineering here at the University of Colorado Boulder. We decided to kick this off to kind of engage our alumni a little bit more in some of the work we're doing here at CEAE Boulder. My name is Carl Linden. I'm the chair of the department. And we have with us Shade Dashti, who's going to be introducing our speaker, and our speaker, Abby Liel. Before we get started, I just wanted to let you all know also we have a new LinkedIn page, and we wanted to find more ways to keep engaged with our alumni, and thought that sharing some of this exciting work we're doing at CEAE Boulder through these types of faculty-led seminars would be one way to keep you informed. In addition, I'm sure you all realize we have an alumni newsletter that comes out twice a year. Hopefully you've heard about this seminar series through that newsletter. And we're really excited that we just launched our LinkedIn page for the department. So we have over 500 followers already in the last month or so. We've had it up and running. And please check out that LinkedIn page. That'll have the latest updates on what's happening in the department. This seminar series is also pinned to the top page of that LinkedIn. So you can check that out and keep updated with the types of things we're doing and highlights from the department throughout the semester and the year. And then obviously, as we send out our newsletters twice a year, those will have a lot of information as well on what's going on at the department level. So it's a beautiful spring day in Boulder. Really happy to have this kickoff today. We'll have two faculty speaker series seminars this semester. We have another one coming up in April, and that's going to be with Ben Livna. And today we have with us Abby Liel, and I want to introduce our Associate Chair for Administration and Professor of Geotechnical Engineering, Shade Dashti, who will be introducing our speaker today. So thanks, Shade, and thanks, Abby.
Thank you, Carl. Good morning, everyone. Thank you for being here, for joining us. And I want to especially thank our speaker, Professor Abby Liel, for agreeing to kick off this seminar series and sharing with us her research over the past decade. So I'll first introduce Abby, and then that will be followed by Abby's presentation, and then we can have questions. And for the questions, you can either unmute yourselves and ask, or type in the chat bar throughout the presentation, and I'll ask those questions at the end. All right, let's get started with the introduction. Abby Liel is Professor of Civil, Environmental, and Architectural Engineering here at CU Boulder. She received graduate degrees from Stanford University and University College London, and her undergraduate degree from Princeton University. Her research examines the risks to buildings from earthquakes, hurricanes, snow loads, and other hazards in terms of collapse and functional recovery, as well as design and regulatory strategies for mitigating those risks. Over the past decades, Abby has actively pursued research that aims to improve building codes and standards, contributing to the advancement of provisions for seismic, snow, rain, climate change, and addressing embodied carbon. She has been the recipient of the Shaw Family Innovation Prize from the Earthquake Engineering Research Institute, EERI. She's a fellow of the American Society of Civil Engineers and its Structural Engineering Institute. Abby also received the James Delahaye Memorial Award in 2025. On a personal note, in the past 15 years that I have been here at CU, Abby has been a friend, mentor, listener, collaborator, and advocate, someone that truly invests in meaningful mentorship for our students and advocacy for our younger colleagues while pursuing research that serves our society at large. She has been a true source of inspiration for myself and many other faculty and students across the department. Without further ado, I'll pass this now to Professor Abby Liel to start her presentation. Abby.
Thank you, Shade and Carl. Let me share my screen. Okay, that looks okay.
Yes, perfect.
Okay. So thank you, everyone, for being here. I am delighted to kick off this seminar series. The nice thing about kicking it off is I'm kind of, I guess, going with what I think you all might want to hear. So I decided that today I would present about one of the projects I've been working on the last few years. And I chose this one because it's really a truly interdisciplinary project and looking at housing, which we all care about, and resilience, which is a big engineering topic and something I spend a lot of my energy thinking about, but also the regulatory side of that. So my collaborator in this work, which is funded by the National Science Foundation, is Susan Osterman, who's a political scientist at University of Notre Dame. So we set out to think about housing resilience in challenging building environments. In the work that what I'm going to talk about today, we've been fortunate enough to do work in Alaska, Hawaii, and Puerto Rico. Most of the work I'm going to show today relates to Alaska with a little bit about Hawaii. But our starting point was really that resilient housing is foundational to communities worldwide. You never find anyone who says, I don't want my housing to be resilient. That doesn't happen. It's really a shared value. We all want safe housing. But we also know that hazards are intensifying and multi-hazard environments can make technical and engineering challenges difficult. So Alaska has severe high winds from extratropical storms. They have a big seismic risk, as well as snow loads and many other things, making it a multi-hazard environment. And Lahaina, we know, has wildfire as well as earthquakes and hurricane events. And so what Susan and I, our starting point was really that, we know that there are people looking at design of housing from a technical perspective in the engineering space, that those solutions are really important, but they're not enough. And that resilient housing also needs attention to social, political, and economic challenges. So we set out to study those things together. So the work we've been doing in Alaska, which I'm going to talk about Alaska, but I hope that you will see elements of this in your daily life. You will see that this is not an Alaska specific thing. So we wanted to look at how people think about regulation. And so we used a series of interviews in a qualitative multi-stakeholder study to understand housing regulation. And here we're specifically talking about building codes and their influence on what is built. We attempt to answer the question, does regulation work? So we look at an observational study of building code compliance, and then we look at how we can design better regulations and enforcement using engineering. And all of these are bringing methods and thinking from both engineering and social science perspectives. So Alaska has, in 2018, had a very damaging earthquake. You can see a picture here of a house that was obviously completely destroyed. There are a number of even brand new houses that were completely destroyed in the 2018 earthquake, which is not what we are intending in our building code. And so it raises the question of how is building code enforcement working there, and what is its effect on the resilience of the homes we live in. So in our multi-stakeholder study, we talked to people with many perspectives on housing. So we talked to builders, we talked to engineers, we talked to architects, we talked to city officials, we talked to residents, all of which was aiming to get a broad perspective of what are the issues with housing, what are the opportunities, and what is the perception of regulation. So in Alaska, we probably talked to about 50 people. Also, we talked to some realtors, I guess that's important to say, and probably 120 or so total over the course of this project. And what we found in Alaska, and this is important because if you want resilient housing, you need to understand how people are thinking about what they're getting. So first, we find a really high degree of trust in building professionals and their ability to deliver hazard resilient housing. And that's great in the sense that builders are trusted members of the community. There's a high integration, even in Anchorage, Alaska's biggest city, a high societal integration and community aspect where people tend to know a builder, they know an architect, and they're interested in working together on that. But we also find that maybe some of that trust might be a little bit misplaced, in that people are thinking they're building professionals are giving them something that they may not be giving them. We also found, and this probably will not surprise you, regulation is not popular in Alaska. So most prefer a method of housing safety that has minimal or no government involvement. So they would really rather not have a regulatory process. But they want the outcomes of that regulatory process. So we're really trying to understand how can you get resilient housing in a place where regulation itself is contentious, but the outcome, the thing that regulation is trying to achieve, is not contentious. And then building costs are very high in Alaska, as is poor quality existing building stock from certain periods. So those are significant obstacles. Very early on in our work in Alaska, we discovered that the city of Anchorage has set up a unique experiment. They didn't set it up as an experiment, but they basically, so the municipality of Anchorage, the boundaries of the municipality of Anchorage, this is on the hillside above Anchorage, are very large geographically. But the interesting thing is that regulation is not enforced everywhere. So there's actually an arbitrary boundary where within the boundary, behind my student and I in this picture, building codes are enforced, and outside the boundary, building codes are not enforced. So you have this situation where this neighborhood that we're showing here, where it's mostly new housing, it's all one neighborhood, but across in the middle of the neighborhood, there's an arbitrary line where inside the boundary, you must submit your plans for review and inspection by the city building department, and outside the boundary, you do not have to. And so it provides an opportunity to say, well, what are we really getting from building codes? And we know from, FEMA has sponsored some very large studies looking at the value of building codes, as other people have studied damage after hurricanes and earthquakes and shown that it really does seem that building codes matter. But here we have the case where there's a building code on the books in both places, and we're really trying to understand what is the value or lack, like what are you getting from having a regulatory process where people submit plans to the building department and they are reviewed? What are you getting for that process? Okay, so the name of that boundary is the Building Safety Service Area. The building code applies everywhere, but the processes around plan review and inspection vary. So there's no enforcement in the part that's labeled outside here. And so we looked at all of the houses built in this one community, which is shown on the map here, between 2018 and 2023. So these are all new homes. And we looked at the differences between them. What are they different inside and outside? That's about 80 houses for reference. We also looked at roughly 50 houses built by the same builder. And so that's a single builder who's pretty active in this area. And we looked at their construction both inside and outside this boundary. And so that's another 50 houses not shown on this map because they're not all in their same neighborhood. So then what we did is we said, well, how are we going to know what the characteristics of these houses are? So because the building department isn't required to review many of these plans, there's no established data set of what the characteristics of these houses are. So what we did is we actually used drone imagery to take pictures of all of these homes. And those pictures are really high resolution. It's a whole series of pictures, maybe like 60 per house, that can then be stitched together to produce a 3D point cloud that we could then use to make very fine measurements of particular characteristics of the houses. If you're interested here, we benefited from the lack of regulation in Alaska. You can fly a drone wherever you want, pretty much, as long as you're not on a flight path. So we did actually not need permission to take the images, but we did not include any pictures of people or anything else. So we just measured dimensions. And here you see we partnered with the University of Washington, which has a natural hazards resource center. So they actually were the drone pilots and they flew the drones. This is the student CEAE Boulder recent master's graduate, Brianna Clark, collecting the data. Okay, so we looked at the results. We compared this inside and outside in two ways. We looked at procedural compliance and also engineering. So I'm going to start with the procedural compliance part first. And what we learned from comparing the procedural compliance is that, not surprisingly, where there's enforcement, there's a lot more compliance. So there's more structural plans, there are more change orders, which are documentation of changes that are made to the plans. There's more review, and there's fewer differences between the plans that are available and what we observed inside versus outside. This is really important. Like, you might be thinking right now, well, obviously, where you're not required to submit documentation, obviously there's less documentation. But it's really important for another reason, which is that in the places where there's no documentation, there's absolutely no record of what was built and whether it is resilient or not. And so in terms of the housing market, buying and selling houses, in terms of recovery after a big storm or earthquake event, outside where there's no enforcement of building codes, there's basically very little data on what's there and what would need to, and the value of that in terms of housing resilience. So we see a big information deficit, and not for me as an engineer, but information deficit for this community in that they don't know what they have because of this lack of compliance. The other thing you'll note here is that the PUR 101 form down here, so this is a form that's kind of semi-regulatory, is through the Alaska Housing Finance Commission, or Corporation, I think, Alaska Housing Finance Corporation, which is a major lender in Alaska for mortgages. And they require an energy rating form. And what you see here is that the energy rating form is done with equal likelihood inside and outside this arbitrary boundary. But all of the structural resilience things are not done with equal likelihood. And so this points to an opportunity maybe to do something more like the energy rating forms and get at some resilience issues, which they're not currently doing. In terms of the engineering, so we did all these measurements of all these homes. I think it was like 80 measurements per house. And we decided what to measure based on engineering. So we measured things that we knew mattered for seismic and wind resistance. So that includes the length of walls, the number of walls, the shape of the roof, the number of stories, etc. And one thing we do note is that the houses were a little bit bigger inside the building safety service area as compared to outside. So there tended to be more stories and tended to have a little bit more square footage. But the primary thing that we found, which is not necessarily what we were expecting to find, is that the houses inside were much more complex. So on the top middle plot here, we have hip roofs and gable roofs. So this is saying that inside the building safety service area, a hip roof, which basically has 4 sides, about 50% of the houses have the biggest roof is a hip roof, and outside about only 13% do. So this is an indicator of complexity. Hip roofs are harder to build. They're also more resilient in the face of high windstorms because they tend to have more, they have more support and they're more redundant structural system. So we're seeing a really pretty big difference here that's statistically significant. We also looked at roof complexity. So in this, we basically counted the number of roof lines that each house had. And we see this big difference in complexity. So nearly double the number of roof lines inside versus outside. So new houses being built in this area of Anchorage inside the BSSA or the Building Safety Service area have a lot more, 12 intersecting roof lines over the course of this house, and the ones outside have 6. We also looked at some measures of seismic resilience. So this number of reentrant corners is the number of ways the house deviates from being a box. It's important for seismic performance. And here we see there's more deviation from the box inside versus outside. I'll note here that I'm only showing results for that one community on the hillside, but interestingly, we found the same thing from that single builder. So there is a builder in Anchorage that is building this very different things on either side of this arbitrary line, in that they are also building more gable roofs, fewer hip roofs, and more complex roof lines when they're within the area where there is regulatory enforcement versus where they're not. So one of the things, our primary finding is complexity. It's not really it doesn't really tell you directly, is that good or bad? But what we think is that builders are probably partially compensating for a lack of engineering in where there isn't plan review and inspection by building one-story and boxier structures. And we know that they're missing some hazard resilient features, like hip roofs, and also introducing some problems related to soft doors and open fronts that they're doing without engineering, or without the guarantee of engineering when they're outside this arbitrary line. So then we spent a lot of time trying to figure out, well, what does this mean and why does it matter? And we have presented these data to a bunch of stakeholders in Alaska and to try to get their feedback on this. And there seems to be quite a bit of agreement that these are our primary mechanisms. So one is a kind of a liability and risk aversion. And so that here are the ideas that there's this added value from a building department, which is that they are protecting, they're in some ways protecting the builder from liability, either kind of in a specific sense or kind of just in a general sense, because the city is signing off on the engineering and the builders in a way that they are not, where there is no building code enforcement. And so we see maybe some conservative design choices where there's more limited regulation because there isn't that additional level of review and sign off related to liability and risk aversion. We also think that there's quite a bit of actually collaboration. So people, and you may have an experience with the building department, it tends to often get portrayed in a contentious manner. Like I go and they told me I can't have my bathroom in this location, or I have to redo the electrical on all my house or whatever. But what we see too is that there seems to be quite a bit of collaboration, by which I mean positive back and forth through which the building department and the engineering or building team are enabling more roof lines, more complex design choices through that collaboration. So on the liability side, my colleague that I'm working with is a lawyer and a political scientist. We see that there's some concern about lawsuits, and there is some evidence of those in Alaska, in the Anchorage region, but also that there's this pressure to provide good housing, and where they don't have the sign off of the building department, they're going to something simpler to ensuring they're providing resilient housing, or to get close to that. And that's sometimes called social license pressure. The collaboration hypothesis, I think, is really interesting for those of us in the engineering space. And what we see there is that the regulatory process is actually guiding design choices. So it's not just that it's reviewing, it's not merely punitive, but that it is driving design choices and driving them in a way that is enabling things. So it's not only saying you can't do things, but it's enabling these more complex building structures. And so there's evidence that professionals that are new to Alaska are socialized to local concerns and designed by building department staff. And that there's a lot of engagement by the building department staff in improving the designs. Now, some people we talked to hate that, and they said this is like, they're turning it into a science project. It's not a science project. I'm trying to build my house. And other people said, I never would have known that I needed to do this thing if I hadn't had like meeting after meeting after meeting with the building department staff. I talked about that we're working in Alaska and Hawaii. One interesting thing is, though, just the political context in Alaska and Hawaii is very different. If you talk to people in Hawaii about building regulation, they're pretty much like, yeah, I wish it didn't cost so much. It was just faster, but I'm generally fine with it. And in Alaska, they tend to say it's terrible, but they all want resilient housing. And what we found actually is beyond that difference, everything else is pretty much the same. So even though there's this perspective about housing regulation being the problem in Alaska, the end result, which is that housing is expensive, exists in both Alaska and Hawaii with almost no difference. So we don't actually see any evidence that it's the regulatory process that is adding a lot of cost to the housing process. There are things that make housing in Hawaii and Alaska really expensive. One of them, and this is also relevant to Puerto Rico, one of them is a source of regulation, but it's not about housing regulation. It's a shipping regulation. So if you are not familiar, the Jones Act is a shipping law that requires transportation between U.S. ports to be on U.S. vessels with U.S. crew. And as you might imagine, what that means is that if you are shipping materials to Alaska and Hawaii, You have to be on a US boat. That means in Hawaii, for example, you cannot take advantage of boats that are going back to China or other places in Asia empty, having brought goods to the US. And so our argument is actually that it is a form of regulation that's contributing to high housing costs, or partially contributing in some of these locations, but it's probably shipping much more than it is about the building department and the regulatory process. To go back for a second, we thought about economics. So people kept saying, well, maybe there's something different inside and outside. Is it cheaper to build outside the building where there isn't regulation? No, it's not. The price of housing is exactly the same per square foot. So we went through every possible economic argument that we could come up with, and we really can't find evidence that there's an economic reason why people are building boxier structures. The only possible thing that we've identified so far is that builders may have more of a profit when they're outside that building enforcement area. I'm not sure about that. We don't have the data to say whether that's true or not. So the policy implications, unsafe housing isn't desirable, or not resilient housing. Nobody wants that. And it's also not really affordable housing. Everybody wants both of those things. And so we are borrowing from this idea of regulatory pragmatism to suggest that housing resilience needs the benefits to be made more apparent to consumers. Our study, we didn't go seeking to identify the benefits of regulation. We thought we might find some engineering benefits, but we found a lot of other benefits too. And so we're trying to figure out how that can be utilized more effectively. There's clearly an opportunity to simplify and clarify the regulatory requirements and process. And we also need to think more broadly about the factors that are causally connected to high housing costs. So on the topic of the simplification, we've also done a number of engineering analyses to try to think hard about what those simplifications would be. And to do so, we modeled 18 different houses, and we informed this based on what we were seeing was being built. You can see this is like the first floor plan. And we looked at 1- and 2-story houses, and we looked at varying levels of code compliance. So we basically looked at designs that were consistent with what we're seeing being built, where the building department has a role, and also what we're seeing being built outside that area. So we did a bunch of field work on building practices to define these houses. And then we did, and this is kind of more traditional engineering, we made simulation models of each house. We subjected them to recorded ground motions from earthquakes and did dynamic analysis. And we carefully calibrated all of our material models to make sure we were capturing the key variables from the perspective of performance. So I just wanted to show a few things about what those results look like and what we think we can learn from them. So on this plot, I've got story drift demands on the y-axis, which is an important measure of seismic performance. More deformation is worse. And I'm comparing it between the 1- and 2-story houses, and each of these lines is a different building and its performance as a function of ground shaking intensity. And so the important thing here is that the 2-story results are higher in almost all cases than the 1-story results. And certainly when you have everything else being the same and you're just changing 1-story to 2-story. And that's pretty critical, because it means if you had, let's say, limited capacity per plan review and inspection, if you were a building department, you would for sure want to focus on the 2-story cases, because we in general see, based on the things that are built, greater impact from lack of compliance in the 2-story housing than in the 1-story housing. We also looked at what variables matter. So here I have 2 things highlighted with orange boxes: brace wall line spacing and brace wall line length. This is suggesting that if you're worried about kind of lower shaking intensities, it really comes down to the walls. Where are they, and do you have enough of them? Just as a side note, there are certainly houses in the Anchorage region that do not have enough walls, where there's not requirement that those be explicitly designed and inspected. So saying that, you need to make sure you have enough walls. And then once you get to, like, if you're more worried about collapse at larger shaking intensities, then you get to some other variables that matter for strength and deformation capacity. So things like hold downs which are metal straps at the bottom of walls, and nail spacing, which is these are nails that are connecting the sheathing to your studs. That those are going to be critical. So we were trying to use this analysis to show, like, hey, like, you know, the building code is, I don't even know, 1,000 pages long, let's say, in a round number, and that's fine, but some of those things matter more than other things. And if you have a case where you have fairly limited capacity, either in terms of appetite for regulation or in terms of just like human capacity to do the regulatory process, that you would want to focus on the things that are most critical from the perspective of housing resilience. And we know that regulatory capacity is a big challenge. We met with the state fire marshal in Alaska, who's responsible for building codes in most of the state, not in the city of Anchorage and a few other cities, but almost everywhere else. And we said, one of our questions was, what do you need to do your job better? And he said, I need an airplane because I just cannot get people to the right places to do the inspection as many times as I need to do inspections. And so this is like relating to like commercial and residential properties across the state. So, you know, what we're trying to do in this engineering study is show that you can use engineering to say like, okay, well, all these things are important in the building code, but maybe some of them are more important than others. And you could use that analysis to design a regulatory process that is getting at those critical issues more quickly. That's my last slide. I will say that we are working, trying to support the city of Anchorage. They're currently thinking about providing optional plan review and inspection outside the building safety service area. And so we're trying to support them in developing a policy that would enable that. We've also had a number of meetings with the Alaska Seismic Hazards Commission, and they're interested in understanding how our work supports some of the bills that they're considering, supports or does not support some of the bills that are being considered on the Alaska state legislature. I will say one thing that's amazing about working in Alaska is that people are really open and friendly and really willing to tell you what they know and to hear your feedback. I mean, we went to the building department on the very first day in Anchorage 3 years ago, made a friend, and that guy has now retired, but we have this whole community of people who are dying to know what we've learned. And we went and told them, like, look, like, we don't know what we're going to learn. Like, it might show that your building department is doing amazing things, and it might show that you guys really have some work to do. And they were like, fine, we really just want to know what your study shows. So they've been really receptive to what the science and engineering is showing about what they could do differently. So I'll just stop there. We are very grateful to the National Science Foundation for funding for this, and to a number of former CU students, Maria Jose Echeverria and Brianna Clark, and a number of Notre Dame students who contributed a lot to this work. Thank you.
Thank you, Abby. If there are any questions, please use your, you can unmute yourselves and ask directly, or type your questions in the chat bar and I can ask. While everybody's thinking, I'll just ask one question, Abby. For the hazard resistant housing that you considered in the options that you considered in Hawaii, did you look at cost and other indirect economic barriers for those options in that particular research as well?
Yeah, so in Hawaii, we haven't done any modeling yet, but we've done a lot of interviews in Hawaii. And we do know, I mean, obviously, if you add things like hurricane straps, which tie your roof to your walls, that does it, you know, the hurricane straps are not free. But we also know they don't cost that much. And interestingly, we saw a number of places where they were put in incorrectly in Hawaii, also in Puerto Rico, but in Hawaii, which to me is like, I don't know, whatever it is, the opposite of an optimum solution, because there you're actually investing in some aspect of the cost that you need to get resilience, but you're probably not getting it because you're doing it wrong. And so we think there's a big opportunity to make sure that where these technologies are being used, they're being used effectively. Hawaii, the county of Maui, has a fairly robust regulatory process. Their main challenge is it takes a really long time. So it's like 400 days to get a permit done, which has its own set of enormous barriers and costs just from the time. And so they're actually working to reduce that time. I think that's going to be critical. That's an indirect cost, but I think that's a critical barrier for them, is the time that review is taking in at least the county of Maui. I can't speak to some of the other Hawaiian counties.
Thank you. Any other questions? There's none. I'll ask one more. Were you able to identify any? I know you were mostly characterizing the structure, the superstructure, any foundation issues in either Alaska or Hawaii that you were looking at, or other forms of like geohazards that stood out as you were collecting the data?
Yeah, in Maui and Lahaina, they've got a complex soil situation where some of the houses are built on volcanic rock and some are built basically porous volcanic rock and some are built on soils. And so there's a real mix there. And I think challenges probably some with the foundation, but also with the water service and the sewer and septic systems, having because of the local variability in soil conditions leading to very different kind of infrastructural solutions in general across different communities. In Anchorage, there's a lot of sloped housing sites. And so we did see, I have concerns about, I can't prove these, but I have some concerns about the ways in which multi-level housing is being built in places where they're not doing any engineering and whether that's being done safely. And then not so much in Anchorage, but other places in Alaska, there's a big concern with changing permafrost locations and how that leads to different foundation designs and the need to have flexible foundations. So that's definitely a big issue across Alaska, less so in Anchorage, where there's less existing permafrost.
Right. No, if there are no other questions, maybe let's give it one more minute in case other questions come up. I'll think of more. As you were defining hazard and risk in these cases, you were looking at a single hazard, right? You weren't mixing, for example, in the case of Hawaii, fire with seismic or other hazards combined.
We didn't combine them in our analysis, but we were considering when we were looking at the things that are built, we were considering how those things are affecting seismic, multiple aspects of resilience. So the fact that it's multi-hazard does create additional challenges because there's maybe some contradictions or just a lot of things to think about. So we did consider that aspect of things, but not in the analysis directly.
Okay. All right, there looks like nobody had a question. Well, thank you. Thank you all for being here. Thank you, Abby, for taking the time to present. And we will send other notifications, as Carl mentioned earlier, on our next alumni seminars. Have a great rest of your day. And please reach out to Abby if you didn't get a chance to ask questions. I'm sure she would be happy to answer over email or other means. Thank you, everybody. Enjoy the rest of your Monday. Thank you, Abby.
Thank you.
Thank you.